Okay, we're recording. Okay, so last time we were talking about how the fundamental theorem of calculus, which you'll recognize in a form anyway here, actually kind of gives us some nice guidance on how to interpret Green's theorem that we just talked about, and also the two-dimensional divergence theorem. So in particular, if you look at the role that the derivative plays here, and I made the case last time that you can think of the derivative pretty literally as being a density, right? It is the accumulating quantity of change per unit size of the piece of the domain that you're looking at. Quantity per unit size, that is literally what density is, right? So I encourage, among your many other points of view that you have on the derivative, thinking of it as change density, and certainly in this context, change density. Okay, so in particular, now of course we can draw this function f, and graphs are wonderful when we can draw them, and it really brings to life a couple of key points. So first key point that we talked about is, I've been making this pitch to y'all for a couple of days now that even though circulation is computed on the boundary, I claim it's actually happening in the interior, right? So this idea that something is computed on the boundary and I'm claiming it actually happens in the interior seems a little suspicious, a little, come on, you gotta be kidding me, right? But look how clear the analogous point is in this case. Change, right, the accumulating quantity for the fundamental theorem here, change is computed on the boundary, right, pretty clearly. That's how you compute how much some function has changed. You look at the values at the endpoints, right? The computation is purely on the boundary. And yet, very, very clearly, that's not where the change happened. Come on. Where did the change actually happen? Well, look, it happened where the function was getting bigger, where it was literally changing, right? So I think this really helps with this big ask that I'm making of y'all, that you even though circulation is computed on the boundary, that I'm asking y'all to think of it as happening in the interior. So highly analogous to what we have here, where again, because of the low dimensions, because we're looking at a graph, we can really see that this is unquestionably the case here. Okay, so I like this analogy for that reason. The other reason that I like it is it illustrates very nicely that these densities not only could persuade you that the accumulating quantity is happening on the interior, but specifically they point to how much and where. Right? So how much change is happening, for example, at, let's say, this value of x right there? Well, I mean, nearby anyway, the function is changing significantly. Right? Now, from a single variable calculus graph point of view, it's because there's a steep slope there. Right? From a algebraic point of view, it's because the derivative is large there. And now saying that latter statement with a density sort of twist, there's a lot of change happening here because change density is large there, right? So I think that's also really nice. Again, it's geometrically very satisfying in this graph picture concerning the fundamental theorem of calculus, but we get these analogous interpretations in the case of these other theorems. And so we talked through last time if we take these ideas and apply them to Green's theorem, circulation, we compute it on the boundary. Well, sure, right? That's where you measure circulation, but I propose that's not where it's actually happening. You can kind of see that circulation is happening in this range here, right? You can even see how the fluid is pushing less hard kind of on that side and more hard on that side, and so we expect this thing to have a counterclockwise sort of rotation about it as it slides toward the right, right? All the field lines are going to the right. So the leaf is actually going to flow down the river exactly straight horizontally to the right, but it'll be twisting, while it does so. So all this circulation you're seeing on the boundary is actually happening where this phenomenon is happening, and it's in this region here. And the dead giveaway, the algebraic giveaway, would be that Green's operator will be large, positive, in that region. Okay, so that's where we ended last time. Now I'm going to make an analogous observation about divergence and flux. So let's see, I guess I have to zoom out to put this all on. Flux, by which I mean outward-oriented boundary flux, of course. Here's how you compute flux. We observe flux on the boundary. Right? That's the computation happens on the boundary. But I propose, again, that's not really where the flux is coming from. You can see the flux actually happening on the inside. And in particular, if I were to look at, let's say, a little region right here, well, there's just as much fluid going in as there is going out. There's no flux happening there. Likewise, if we were to look at this region, let's say there, well, again, there's just as much fluid going in as there is going out. Now, there's more fluid going in and more fluid going out, but again, to the same degree, in the same amounts. Right? So that's not where divergence is happening. All this that's not where the flux is happening. All this boundary flux that we see in purple, where that's coming from, it's coming from in here, this gray region, where, yeah, there's some fluid going in, but then there's clearly more fluid going out, right? Because you can see the field line, the field vectors are getting longer as we move to the right. So there's less going in, more going out. We're seeing, therefore, in this picture right here, we are seeing flux happening in the interior. Again, you measure it on the boundary. It's actually happening in the interior. And so again, this would, this phenomenon is happening here. That's where that's where the flux is actually coming from, and that would be algebraically evidenced by the divergence in here being positive. And outside of that gray region, the divergence would be 0. Okay. All right. So, again, strong analogy, really nice interpretations that we get out of just applying some of the same ideas. Fundamental theorem of calculus, our old friend that y'all all know so well. Okay. All right. Not just an algebraic sort of manifestation of these ideas. Here's a vector field. We're going to look at this rectangle, and in particular the boundary of that rectangle. And so we have a closed curve, and we could talk about then how much circulation is there around that closed curve. And we could talk about how much flux is there through that closed curve. And those are computations. You can compute what those amounts are, and it doesn't really matter for the purposes of this problem. For this problem, I want to ask, is more of it happening at this point, or is more of it happening at that point? So this is analogous to this example that we did here last time, where I asked, okay, sure, there's a bunch of change happening. Is there more change happening at 1 or at 2? Right? Where is there more change happening? Well, the obvious answer here was, well, yeah, look at the slope, right? Look at f prime. How steep that slope is the giveaway for how much the function is changing. Let me say that differently. The change density is the giveaway for where the change is happening. Right? And so, you compute that change density, and you plug in and you see which one's bigger. Nothing to it. So likewise here, if I want to know where more of the circulation is happening, well, I'm going to compute circulation density, and compute that circulation density at the green point I'm considering, at the blue point that I'm considering, and I'm just going to see where is it bigger. And, well, it appears that it's bigger at this point here, 2, 4. So there's a certain amount of circulation happening that you would witness on the boundary. More of it is coming from 2, 4 than is coming from 3, 3. Now, I can't really draw a very good picture of this for you, right? But it's totally analogous to the picture that I can draw in this previous example of, greater density, more stuff that we saw here. Okay. All right. Likewise for the divergence, totally analogous. Again, looking at this green point, this blue point, where is there more flux happening? We will look at flux density. We will compute that flux density at the green point, at the blue point, and see which one's bigger. Now, in this case, this time it happens to be 3, 3, where the flux density is greater, and so more of the flux is coming from 3, 3 than is coming from 2, 4. Is everybody on board? All right. It's a really nice interpretation. Okay, and now moving along, section 6.3. By the way, I did assign 6.2 for the homework for last time, because all of this stuff that I'm doing here is kind of supplemental to what's happening in the book. Shouldn't affect your work on any of the exercises. So as far as homework was concerned, we were done with 6.2 last time. Okay, so moving along. There is another theorem that's a lot like Green's theorem. And it's also a lot like the fundamental theorem of calculus. So a lot like those theorems, not just cosmetically, but in that it's a theorem about an accumulating quantity that is computed as an integral of an associated density. And so it's called, here it is, it's called the fundamental theorem of line integrals. And cosmetically, it looks tremendously like the fundamental theorem of calculus, right? Just on the page, wow, it looks exactly the same, right? The difference here is that this function f is now a multivariable function, not a single variable function, right? These points A and B are now points in space. Well, the plane or space or Rn or whatever your domain is, and the integrand of the associated integral is a vector field. This being then a vector line integral. So it's a different theorem, right? Definitely a different theorem, but still cosmetically. Integrals computed as a difference, and the integrand is a derivative of sorts. In this case, it's a gradient, right? So it's definitely a different theorem, but very similar. Earmarks, right? Cosmetically. Okay. Terminology thing, by the way, while I'm here, I'll just mention vector fields that are gradients are very often called conservative. I think this is a weird word choice because there's already a word for vector fields that are gradients. The word is gradients. I don't really see why we need the word conservative, to be totally honest. And the motivation for this term, by the way, it has to do with physics. It's got to do with conservation of energy, related ideas of potential energy, right? And if you want to make good sense out of those concepts, the vector field being a gradient is important, as it turns out. And this is not a physics class, so I'm not going to go into that. But that's the motivation. Okay, so let's talk about the theorem, though. Why is this theorem true? And I claim again that it's just an accumulation. There is an accumulating quantity. The accumulating quantity is change, just like with the fundamental theorem of calculus. I claim that change is an accumulating quantity. You can see it in action right here if you're looking at this curve and you ask, what's the total amount of change on that curve? Well, I can break that curve up into little pieces. Well, I'm just going to do 2 pieces here. I can look at the amount of change on that first piece, and I can add to that the amount of change on this second piece, and observe conveniently, these two terms in purple cancel. Right, same term, opposite sign, and all that's left over is exactly what it's supposed to be. So it's easy to prove that this is an accumulating quantity. Nothing to it. It's also pretty easy to just kind of buy it. Right? Again, as you were driving along a road, keeping track of your altitude change, let's say, as you drive along the road. The total altitude change is the sum of all of your incremental altitude changes. I mean, again, it's just, of course, right? Okay, so change is an accumulating quantity. And we can talk about the related notion of a density. So if I have a little piece of curve, and keep in mind when you have a little piece of curve, there is an associated dx vector. Right, and if I want to know how much does the function change, what is the total output change of the function? Well, flashbacks to chapter 2. Output change is the gradient vector dot input change. Oh, you know what? I just trampled the little. Okay, there we go. So output change, gradient dot input change. And if you rewrite that a little bit, notice I've rewritten it like here, and all I did there is rewrite dx as tds, and that's an old chapter 3 fact, right? So flashback to chapter 3 if you want a reminder on why that's true. But anyway, having written it like that, notice that I can reinterpret this as change, output change, being a multiple of, green highlighter, input change. So the thing that you multiply by size to get the accumulating quantity per unit size, again, that's a density, right? That's our fundamental notion of a density. So gradient dot t, wrong color, sorry, confusing color choice. Gradient dot t, as it turns out, is our related notion of density. This is what you might call change density in a multivariable context. Okay. All right. Now, real quick, I want to point out this is a nice point of view. It has its moments. So I first focused on the idea of quantity in relation to size, because that's how density works. Right? But now let's look instead at quantity viewed in kind of the way we first wrote it down. Right? And so now this thing here is dx, is not size exactly. I mean, dx tells you two things. Its magnitude is size, but it tells you more than size. It also tells you which direction is that little piece of curve pointing, right? So we say that it's an oriented thing, right? Orientation means it's an indication of which direction something's pointing. So I'm going to stretch our vocabulary a little bit and ask for some flexibility and interpret dx as being oriented size, because it does tell you size. The magnitude of dx is the size, but it's also telling you a direction. The direction that little piece of curve is pointed, thus an orientation. So if you view that as being oriented size, now let's think about the semantics again. If density is what you multiply by size to get quantity, wouldn't it seem reasonable that oriented density would be the thing that you multiply by oriented size? And so that's the concept that I want to sort of throw at you here real quick. This is just kind of an interpretation, so I'm not proving anything here. It's a way of thinking about the gradient vector. Given this formula that we have highlighted in blue, I think it makes sense to call gradient an oriented density. And we're going to come back and talk about that more later, but for the moment I just wanted to throw the term out there. So adding all of this up, you can take your accumulating quantity of change. And let's see here. I'll use first that formula for change, right? Thus giving us this theorem that says that change is this integral here, and that's a fine way to think about it. Nothing wrong with that. You can see the corresponding change density right there in the integrand of that integral. So cool, fine. But now notice I could instead think of this a little differently. I could instead think of change as computed from these oriented density and oriented size, right? Thus giving us this version of the fundamental theorem of line integrals, where the integrand is now, oh, come on, sorry, my stylus is a little weird. Oriented change density is your integrand. Okay, so it's just a point of view. Take your pick. For whatever it's worth, I mean, there is some really nice stuff about this point of view on this integral. I mean, for one thing, it's less pencil strokes, right? It's more compact. It's evidently and visibly a vector line integral. I always believe in being as overt as possible, distinguishing what something really fundamentally is, and trying to conceal a vector line integral as a scalar line integral, I think is, I don't think that's a good idea at all, right? So I have a significant preference for this phrasing of the theorem. Okay, is everybody on board? Any questions? All right, let's do one. Here's a vector field. Here's a curve. Compute the line integral. Now I want to point out something about this theorem before we actually find an answer for it. Notice in the statement of this question, it does not direct you to how to solve it. Right? It doesn't say, hey, by the way, use the fundamental theorem of line integrals. Right? It just says, compute the line integral. And now it's your job to figure out what theorem you're going to use to compute this, right? And we know a few, by the way, right? One theorem that we know for how to compute line integrals is to parameterize and, do that whole business. And in fact, not only is that an option, the statement of the question is almost kind of nudging you in that direction because the parameterization is given, right? So you would be forgiven for, at a glance, sort of maybe initially thinking that, oh yeah, I should plug in the parameterization and plug and chug. And that would work. You could do that. But here's a much better solution. Much better solution is to observe that this vector field is a gradient. It is a gradient of this function that I can just directly write down. Now, real quick aside, how did I know x squared, y squared? Where did that come from? That wasn't given in the statement of the question. Did I just pull that out of thin air? I mean, I can confirm that this works, right? The appropriate partial derivatives are what they're supposed to be. But where did I get it in the first place? Reasonable question. And I will tell you later. For the moment, I'm going to hold my cards on that and focus on other things. But we will come back and talk about how to find this thing. But observe, this is very reasonably an anti-gradient, you might call it, right? In the same sense that if this were a single variable calculus problem, that would be the antiderivative. So I like the term anti-gradient. Another cultural point, heads up. Apologies, anti-gradient is not the more common term. The more common term is potential function. I think I griped about this a few weeks ago. So you're going to hear the term potential function more often. I think anti-gradient makes loads more sense. Okay. Anyway, once you have your anti-gradient, you're in business. We can compute this line integral we've been asked. Oh, well, that's an integral of a gradient. We have a theorem that says if you want to compute the integral of a gradient, cool, f of b minus f of a. Just plug in the endpoints into the anti-gradient function. And this is easy arithmetic, right? Just plug in these points. A goes, actually, let me do it like this. A, our starting point, you plug into there. B, our ending point, you plug into there. And the integral, fundamental theorem tells us it's f of b minus f of a. And plug and chug. Everybody happy? Real quick, while I'm here, I want to point out where I got these endpoints from, right? How do I know that the point that this curve starts there? And I know it starts there because I can see the parameterization. It says right here that t starts at 0, and when t is equal to 0, x and y are 1 and 0. Okay. All right. Likewise for the endpoint. All right. So very nice theorem, very useful for computing line integrals. Now I'm going to talk about a related idea that will not appear to be related. We'll get to the connection in a few. But seemingly here, fresh start, new idea. I want to talk about an idea called path independence. Some vector fields have this remarkable property of being path independent. It almost seems like it shouldn't be possible. Here's what it is. A vector field is path independent if the evaluation of a line integral only depends on the endpoints, and the curve makes no difference at all in between those endpoints. And this seems highly implausible. I mean, if this were the case, why did we go to all that trouble to compute line integrals through parameterizations, right? It just seems outrageous to suggest, oh yeah, it turns out the curve doesn't matter. Come on, how could that be, right? So highly implausible, but nevertheless, this is what we call the property of path independence. I emphasize path independence as a property of the vector field. So the vector field is what is path independent. I do not care for this phrasing right here. Has path independent line integrals. I think this puts the credit for path independence on the wrong thing, right? So path independence is a property of the vector field. This makes it look like the adjective path independent is referring to the line integral. It shouldn't be. It's the vector field specifically that has this property. So anyway, that's a little beef of mine. Anyway. Everyone who says this phrase knows perfectly well that they're talking about the vector field, but anyway. Okay, so just to write it down formally, when we say the path doesn't matter, what we mean is as long as your two curves, C1 and C2, start and end at the same point. So, for example, let's see here. Here's a starting point. Here's an ending point. And that path and that path have the same start point. Let's see here. Same starting point, same ending point. So on a path-independent vector field, the green line integral and the blue line integral would have to be equal. And again, outrageous suggestion. How could this be possible? There's so many different curves, for crying out loud. Oh my gosh, there's a bazillion of them. You're telling me then that not only will those two be equal, but also this? Well, also, yes, it will also give you the same value for the line integral. It seems outrageous. Okay, now just to emphasize how implausible this sounds, so this is just for intuition purposes. Here's an explicit vector field. Let's see here. Here we go. 0, x. I mean, innocent-looking, unremarkable vector field, and you can draw a picture of it. Here you can draw several vectors there, and now let's consider a couple of easy, unremarkable, nothing tricky curves. Here's one curve, Here is another curve. Notice that both of these curves start and end at the same point. So they both start at the origin. They both end at 1, 1. I mean, would I expect these line integrals to be the same? No, come on, get out of town. Look at this. Is really easy to compute, by the way. On that edge of C1, that's sort of the first half of C1, the vector field itself is 0. So there's not going to be any line integral there. On this second edge, the dx vector is horizontal. The field vector is vertical, so the dot product's going to be 0. So there's no line integral there. So on the green edge, the line integral is clearly 0. It's just a matter of breaking into those two pieces. And now let's look on the blue curve. On this edge, again, orthogonal, dot product is 0. So there's nothing there. But on this edge, the line integral is positive. The dx's are pointing up, the field vectors are pointing up, the dot product's going to be positive. So on this blue curve, we have a clearly positive, clearly not 0, and therefore these are clearly different. Yeah.
Wait, I'm confused because we were just talking about the fundamental theorem of line integrals that it's...
Yes. Well, you're getting ahead of me.
Okay.
You're getting ahead. I know where you're going. That's a great observation. That's the very next thing we're going to do. So the purpose of this example is I want students to have a very crisp and clear idea of why you would not initially expect for any vector field to possibly have you're telling me you're going to get the same value for the line integral for all curves. I want it to seem implausible, right? Because it is kind of outrageous. But no, you're exactly right. That's the very next place. Oh yeah, sorry, go ahead.
I don't really understand how you got how 1 was equal to 0.
The green one?
Yeah.
Okay, well, it's just a matter of, first of all, you can straight up compute this, right? You can literally parameterize each of these pieces. This is an easy piece to parameterize. This you can totally parameterize. But the argument that I made is that here, well, the vector field is literally 0, right? Because x is 0, and if x is 0, then the vector field is flat 0. And any integral of 0 is 0, right? And then on this edge, the point is a vector line integral involves a dx vector, which points that way, and then the field vector, which points that way. And that's a right angle, and so dot product 0. Yeah, exactly. Okay, so now hopefully you're willing to believe that it is an outrageous suggestion that any vector field could possibly be path independent. And with that in mind, now let me show you some vector fields that are path independent. And I'm pretty sure this is exactly what you were going to say. So in fact, not only is there a vector field that is path independent, there's a whole category. All gradients. Now, regularity concerns, I do have to say continuous here, so okay, fine. Every regularity issues aside, every gradient field is path independent. As follows. Suppose you have two curves that start at A and end at B. So as usual, let's take, let's use green for the first one. And let's use blue for the second one. There we go. So we want to compare that green line integral to this blue line integral, which are computed over entirely different curves. Right? Totally different curves. Why would I expect them to be the same? And the answer is that both of these can be computed with the fundamental theorem of, colors again, fundamental theorem of line integrals. That green line integral, we're doing a line integral of a gradient. Fundamental theorem tells me I get this. The blue line integral, I'm again doing a line integral of a gradient. Fundamental theorem tells me this. So these two integrals are equal to each other because they're both equal to the same thing. They're both equal to a computation done at the endpoints. You ready to buy it? It's a real cool little argument. So I like the little intellectual whiplash there of surely you're joking, this isn't possible, to, oh yeah, here's a billions of examples. It happens in about 45 seconds there. I think it's fun. Okay, is everybody happy? Okay, now I am not going to prove the following, but I do need to state this. So not only is every gradient path independent, but it is also true that every path independent field is a gradient. Or said differently, not only is every gradient path independent, but only gradients are path independent. So, here's if you're curious, there's a kind of a sketch of the proof here. You're welcome to take a look. It's not part of the course Math 219. You don't need to see this, but if you're wondering how could this be, then take a look at this. Okay. All right. Now, it's going to turn out that path independence is a really important and useful idea. Excuse me. So it's valuable to note this other way of saying it. Now, same idea. Again, the premise of path independence is that we have two curves that start and end at the same points. So, for example, that green curve and this blue curve both start and end at the exact same points. So, okay, if I were to state that the green line integral and the blue line integral are equal, notice their being equal is totally equivalent to saying that their difference is 0. Now, this is the exact same. This is just the green line integral minus the blue line integral. Their difference is 0. Now let me rewrite that a little bit. I'm going to reconceive of their difference. Their difference, integral on C1 minus the integral on C2, I could think of as an integral on a path that follows C1 and then just keeps going backwards along C2. If you think about it, right? So if you follow that dark blue path, you're going to do all of C1. And then you're going to do C2 backwards. And in effect, then, that total line integral is literally the difference. Integral on C1 minus the integral on C2. Does it look reasonable? So saying that the two line integrals are equal is equivalent to saying that the closed line integral, the line integral on that loop that starts and ends back at the exact same point that it started on, that closed line integral is 0. So this is just, again, an alternative formulation of path independence. If you want to talk about path independence, you can say, well, these two line integrals are the same, or you can say all closed line integrals are equal to 0. So that's how I have it written down here. Closed line integrals equal to 0. You buy it? Okay. Alrighty. Oh, and by the way, the notation, this is a common notation. This little sort of circle in the middle of the integral symbol, that's just a kind of a visual cue to the reader that, by the way, don't forget, hey, this is a closed line integral. The domain for this integral is a curve that starts and then comes back and ends at the exact same point. It's just a visual reminder. You don't have to put that little symbol in there. Some people like to put that symbol in there to kind of help them remember what they're doing, but don't really have to. Okay. All right. So, here's a related example, and I like this one. This is fun. So let me just remind you that we've talked about the altitude function, h. Right? So, given your longitude and latitude, or the coordinates of where you are in some region, whatever, you can talk about height above sea level as a function of x and y. Okay, and now let's think about the gradient of that height function, that altitude function. Well, it's a gradient because there it is. I'm defining it as a gradient. Well, that means that it's path independent, as we recently discussed. And path independent means that all closed line integrals are equal to 0. Now, let's take a look at this statement here. Closed line integrals are equal to 0. And let's remind ourselves, wait a minute, what is it that this integral here on the left is computing? Integral of gradient of altitude dot dx. This is computing how much altitude changes. Right? You can see this in the fundamental theorem of line integrals, coming back to here. Right? Integral of a gradient computes how much that thing you're talking about the gradient of changes. Right? So this integral that we're looking at here, doggone it. This integral that we're looking at right here says how much altitude changes across this path, and of course this is a closed loop, so how much altitude changes as you go around a closed loop. And according to what we've just reasoned, that has to be 0. Your grand total altitude change when you go on some trip that brings you back to right where you started, your total change in altitude is 0. Right? And despite the old joke about, everybody's grandfather talks about how, I had to walk to school, it was uphill both ways. Right? No, it wasn't. Right? You went to school, you came back, your altitude change was 0. Right? The interpretation I'm going to make of this is that because altitude change has to be 0, Escher stairs are impossible. Now, this was already obvious. Everybody knows that this picture is nonsense, right? I don't know if y'all have seen the works of M.C. Escher before. He's a fun artist who drew sort of like geometric impossibilities. And basically you can lie with art. And he was a masterful artistic liar, right? Lying about the geometry of space. So anyway, fun stuff. But let's think about what he's suggesting with this drawing. In this drawing, if you look at this fellow here, and the people that he's following, seems to be walking up, and then continues that they're walking up there, and then again continuing along, still up, and then as they continue this way, still up. Escher's stairs seem to be going uphill the whole way around. But they can't be, because that's not 0. Right? The total altitude change has to be 0. Everybody see what I mean? So now all we've accomplished here is to basically mathematically formulate the obvious. You don't need to know multivariable calculus to know that this is that's not how it works, right? That's all garbage, right? But what we do have is a mathematical formulation of exactly what it is that's wrong with the geometry that he presents here. Okay. All right. Okay, so now real quick I want to point out a detracting point to the idea of path independence, and that is path independence is usually not a computationally useful thing. Now, in its defense, before I do some negative talk, it is useful conceptually. Very useful conceptually, and again, a prominent use of the idea of path independence is in physics. If you want to make sense out of the idea of potential energy, just real quick, and this isn't a physics class, so I don't want to digress here, but if you want to know the difference in potential energy between this starting point and this ending point, the way you compute the potential energy difference is by computing the amount of work it takes to move from the one point to the other. But what path do you choose? You could choose any path. I mean, if potential energy is going to only depend on location, all paths should give you the same amount of work, thus telling you the same sort of difference in potential energy between those 2 points, right? So path independence is fundamental to the idea of potential energy, which is fundamental to the idea of conservation of energy, which is a pretty fundamental fact in physics, right? So it's really a big deal, very important concept. But computationally, I make the observation that, look, if you have a path-independent vector field, we already know that means it's a gradient. If it's a gradient, we can use the fundamental theorem of line integrals, which is a sledgehammer for line integrals, right? So, why do we need a tool for computing integrals when I already have one that will seemingly always apply, if not just as well, if not better? So there's a strong point there, but I will observe that there are some cases where even though, yes, there is an anti-gradient, sometimes identifying that anti-gradient can be actually pretty hard. So there are some cases where path independence is still a pretty useful idea. Let me show you an example. Now, this example is not a perfect example in the sense that here, finding the anti-gradient is actually not hard. I'm going to, again, show you all how to compute anti-gradients real soon here, a couple of minutes. We could totally apply those ideas. In fact, you might even be able to guess what the anti-gradient is here, right, at a glance. But anyway, it doesn't matter. But let me show you how to use path independence alone. So this vector field is path independent, as it turns out. Take my word for it in this case. I'll show you how I know that in a couple of minutes. And I want to compute the line integral over the top half of the unit circle, oriented clockwise. How do I compute this line integral? Well, and I'm going to re-choose my color to be green. There's the path on which I want to compute this line integral. This line integral, C. I know that my vector field is path independent. Here's how we use the fact that it's path independent. Path independent says I can change any other curve I want as long as it has the same starting point and same ending point. So now again, the starting point and ending point are fixed. They're part of what this green curve is. But what other curve would I like to pick? Instead, I can choose any curve I want. It doesn't matter. As long as it starts there and ends there, we're good. Now, you could choose that path right there. I don't think that's a well-motivated idea, right? Obviously, you're not going to choose something ridiculous, right? We're all trying to save as much time as possible, so we're going to choose the easiest path we can think of. In this case, I think it's hard to argue with a straight line. And so, because of path independence, right, because I know this is path independent, two curves that start and end at the same point are going to give me the same value for the line integral. Everybody with me? And so now I just say, okay, you know what? Phooey on that green curve. I don't even like that green curve. That green curve was annoying. I'm instead now going to look at this blue curve, and let's compute this line integral on this blue curve. And wow, this is easy to do. In fact, I can parameterize that blue curve really easily. No trig. Right? Our original green curve is going to have trig in it. It's going to make for annoying integrals. This blue curve, nothing to it. Right? A couple of really nice things happen here, by the way, further. Notice that on this blue curve, y is 0. It says so right there. Well, that means that everywhere I've got a y, it's literally 0 on my entire blue curve. So I get to rewrite my vector field a little bit. And that's a neat trick. Everybody happy? And then further observation, check it out, all of my dx vectors, right? My little dx vectors are all going to look kind of like that. My dx vectors are all going to be horizontal, it seems. So, in particular, dy is 0. And we're done. Right? The computation of this blue integral here, that integral right there, I mean, I can see right there algebraically in the dot product, 0. Done. Everybody happy? All right. So path independence, it has its moments. Okay, now I started this example with a completely unjustified assertion. I just asserted out of nowhere that this vector field is path independent. And how did I know that? Where could I have gotten that from, right? I mean, what, divine intervention, somebody, how do I know? How do I justify? How would y'all on a test be able to know whether or not you can use the property of path independence? So we have one test already. We already know that, here we go. That if you have a gradient, then it's path independent, right? So that's something to be on the lookout for. Anytime you see a gradient, path independent, you know it. It's nice. But what if you don't know if it's a gradient? And so, such as in this case right here, there's no immediate indication that this is a gradient of something. Now, you could, again, consult your inner oracle and hope that it just kind of comes to you that I see what this is a gradient of, but it's not a good plan, right? Probably not going to work. So here's the lovely idea. This is what I call a local test. I'll explain the motivation in a minute. And we're going to talk about 5 different conditions that I claim are all simultaneous. Again, ignoring regularity issues. We don't want to get bogged down in that stuff. 5 equivalent conditions. And here we go. I'm going to start off with 3 that we already understand. We already understand the connection between these. We've talked about the fact that every gradient is path independent. Every path independent is a gradient. And furthermore, path independence can be reformulated as this statement about closed line integrals. So we already know that all 3 of these conditions in green are all equivalent, right? Everybody happy? Okay. So, so what's the connection between these 2 conditions? And this one's a little tricky, but it actually works out really nicely, and it is as follows. Look at this thing right here. This thing that we're claiming has to be 0. That's a closed vector line integral. Closed curves are boundaries. This closed line integral, then, by way of Green's theorem, is a double integral of Green's operator over the interior. So, those 2 things being equal, if this is equal to 0, then it follows that this is also equal to 0. After all, they are the same thing. Everybody follow that? All right. Now let's look at this statement here. Let me get out of my own way. This statement says that I'm taking a double integral of Green's operator, and I get 0. But wait a minute, this says actually more than that. This says for every domain, no matter what domain you pick, all domains, this domain, that domain, this domain, any domain, big, small, tall and skinny, whatever, any domain of area at all, the double integral has to equal to 0. Now, how is that possible? What function, right? What could this blue function be? What integrand has this feature that all of its integrals are always 0, no exceptions? There's really only one such function whose integrals are always 0, and that is the function that is 0 itself. You buy it? So here's what we've got then. I mean, there was kind of a multi-step process, but what we see now is anytime you have a gradient, Green's operator is going to be 0, and vice versa. So this is what we call a local test. This right here is the local test. We call it a local test because let's see. Let me circle that differently. this is the local test because Green's operator is something that is computed locally, right? Green's operator you compute and evaluate at individual points, right? And we get this global conclusion that there is a single function defined everywhere in space whose gradient gives you the given vector field. One single function whose gradient gives you the vector field at all points, right? That's a kind of this anti-gradient little f is a globally defined thing. And I can detect its existence by a locally done computation. So that's pretty cool. Okay. All right, so what we would do then is if we find ourselves with a vector field, and I want to know, is that vector field a gradient? The way you resolve that question is you compute Green's operator, and you see if you get 0. And if you get 0, then yes, your vector field is a gradient. And if you get something that's not 0 ever, then it is not a gradient. Really nice test. Okay. So, for example, up here, right? How did I know that this vector field was path independent? AKA, how did I know that it was a gradient? Well, I computed Green's operator. The x partial of this is 2x, from which I subtract the y partial of this, which is also 2x. I have 2x minus 2x. That is 0 everywhere, and therefore path independent. Everybody happy? All right, now there is a three-dimensional version of this theorem and argument. So here, this is the two-dimensional theorem and argument. Notice this is specific to R2. The three-dimensional version is here, but uses another theorem that we actually don't know yet. So the magic big step down here in the bottom right where we used Green's theorem, well, there's another theorem that we're going to be seeing in Chapter 7. It's kind of a three-dimensional version of Green's theorem. And just in case you're curious, if you're trying to piece together the puzzle pieces, it's Stokes' theorem, as it turns out. We haven't seen that theorem yet. We'll see it next week. But Stokes' theorem allows us to do that. Okay. So the result, I will go ahead and tell you, argument to come later, is that if you have a three-dimensional vector field and you want to know of that three-dimensional vector field, is it a gradient? Is it path independent? Then what you do is you compute the curl. If the curl is 0, then yes, it is a gradient. And if the curl is not 0, then no, it's not a gradient. So structurally, just like this theorem here. Okay. All right, let's see an example. A couple of examples here, but starting with this vector field right here is a three-dimensional vector field given away by the fact that there are three components. When I ask the question, is this a gradient? We're going to be applying this tool. Right? We want to know whether this is a gradient, so we compute the curl. And you can see I've started this computation for the curl right there. And notice that I stopped after I'd written down the first component of the curl. I was like, well, why'd you stop? Don't I need to compute the whole curl to answer this question? And subtle little tricky bit, sometimes you don't even need to compute the whole curl, because I already know what the test is. The test is whether the curl is exactly 0. And I can already see that's not the case, right? This right here, first coordinate, already clear that that's not 0. It doesn't really matter what the second and third components end up being. Second and third components can never change the fact that this is already not 0, which means our curl is not 0, which means that this is not a gradient. So no. Everybody happy? Okay. Now, just FYI, this clever little observation only works when you get non-zero coordinates. If this had been, hypothetically, let's see here, let me just kind of scratch all that out. Let's suppose that our first coordinate had been 0. Well, does that mean that the whole thing is going to be 0? No. I mean, it's still possible this could be non-zero. It's still possible that could be non-zero. So you basically have to keep computing until you get not 0 or until you're done. Okay. All right. Okay. Here's another example. We've seen this vector field before. Is that a gradient? Let's play the algebraic game. Now, this is a 2-dimensional vector field, right? Because it has 2 components. So being 2-dimensional, we apply the 2-dimensional local test, which is Green's operator. And remember, the Green's operator says x partial of the second coordinate minus y partial of the first coordinate. You punch that up, see what you get, and Green's operator is not 0. And so again, we fail to get 0, and therefore this is not a gradient. Okay, now that's the algebraic take on it. Now let me point out that we actually kind of already knew the answer to this question in some sense, because we already knew that this vector field looks like this, right? This is one of the very first vector fields we ever wrote down back in chapter 3. And remember, I drew this picture and I pointed out that to me it looks like a stirred pot, right, as seen from above, right? And there's, it's like the fluid is flowing around counterclockwise, right? So now looking at this picture, let's just kind of think through, how could this be a gradient? I mean, realistically, could this be a gradient? If it were a gradient, keep in mind, gradients, the vectors point uphill. How could all of these vectors be pointing uphill? This would create an Escher stare scenario. This is clearly nonsense. You cannot have all of those vectors be uphill. I don't care what your grandfather says. Right? That makes sense? So in some sense, geometrically, we already kind of knew that there's no way this could be a gradient. But in the absence of such geometric intuition, this algebraic test, very convenient. Okay. All right. Now, this business here, this is not in the book. Question.
So for the 3-dimensional vector field,
yep.
Does the curl has to be 0 for all values or just one?
The curl. Now, this is a statement about vectors, right? So the curl, that is a vector, has to be the 0 vector, right? Both of these are vectors. And when we say the 0 vector, that specifically means the vector for which all 3 coordinates are 0. Yeah, so there is no, right? If you say, a vector is 0 or a vector is not 0, when you say that a vector is 0, there is no version of that is only a reference to a single coordinate, right? The 0 vector is literally and only the vector where all the coordinates are 0. Does that make sense?
Yeah, so for that example, if we plug in some value for y and z and then the first coordinate just has to be 0, that still doesn't work.
Well, this has to be for all values of x, y, and z, and so I don't need to plug in any values as an expression. I can see that this expression here is not always 0, right? It would algebraically, you can't have a leftover z squared term, right? I mean, you don't have to go to the trouble of finding the x, y, and z that literally make this non-zero. It's just sort of obviously not the 0 expression, and so therefore it's just not 0. Does that make sense? Yeah. Cool. Right, anybody else? Okay, so this diagram here, this is not in the book, certainly not as I've drawn it here. Awkward fact that I have to observe. The take that I'm giving y'all on vector calculus in this class is tip of the iceberg. It turns out there's a lot of really deep points of view on Green's theorem and the fundamental theorem of line integrals and the three-dimensional versions of these theorems that we're going to see in Chapter 7. We have Gauss's divergence theorem and Stokes's curl theorem, etc. So the deep fact is that all of them are closely connected. They're not just analogous to each other. They're literally connected, mathematically connected things. And they're connected by way of some sophisticated constructions, one of which is integrals of differential forms. And you may recall when we were talking about coordinate line integrals, I made a reference to differential forms that are sophisticated, powerful things that you can do good stuff with and that people like for those reasons, but that we won't make any significant use of in this class. So same differential forms. It turns out that all of these theorems that we've seen and that we will be seeing going forward are all connected by way of this very powerful construction, that they are all differential forms and that they're all connected by way of what we call a chain complex and a co-chain complex. And this is not at all Math 219 appropriate. The reason I'm telling you about it is not because we're going to study chain complexes and co-chain complexes, but because the fact that they exist, the fact that all of this more sophisticated stuff exists and works, makes some amazing patterns show up. And these patterns are extremely helpful in Math 219 in keeping track of the various ideas and the various relationships that we have seen and will be seeing going forward. So the way this is going to look to y'all is I'm going to draw this thing I'm calling a diagram, this strategic diagram, where I'm going to take the gradient operator and fit it in like Legos with Green's operator, seemingly arbitrarily. It turns out this is not arbitrary. This is a co-chain complex. And again, this is all very mathematically natural, as it turns out. There's good reasons for why we do this. Again, we can't talk about. So what we're going to do here is I'm just going to draw this diagram and say, hey, guess what? If you think about everything in vector calculus as fitting together on this diagram, the pieces will just fit. Things will just work. Patterns will evidence themselves. It'll make it easier to remember various results. It'll make certain things that you might sort of hunt your brain for possible ways to make sense out of. But this diagram will mean, it's obviously false. So lots of convenient benefits that come out of this. So here's a couple of them. First of all, let me first start with Green's theorem. Green's theorem, you see I have right here. You can think of this as the following pattern, that I start with a vector field and I compute Green's operator. And I could then think of it that there is a region for which I compute the boundary curve, and then if I do a line integral of over the boundary curve of the original vector field, and if I compare that to the double integral over the initial region of the resulting Green's operator, then I get the same thing on both sides. Now that's just a sort of a pattern of how the objects that are involved in Green's theorem, how do they sort of fit together on this diagram as I've drawn it here. And let me sort of streamline this, if you will, as Green's operator goes that way, boundary goes this way, you evaluate on both sides, and you get the same thing. Now, let me do the same sort of diagrammatic manifestation of the fundamental theorem of line integrals. For the fundamental theorem of line integrals, we take a function and look at its gradient field. We take some curve and look at its boundary points. And if you evaluate the original function on those boundary points, or if you do a line integral of the gradient vector field on the original curve, you get the same thing either way. Notice it's the exact same pattern. Right? Just the structure of what it looks like on the diagram, exactly the same for these two theorems. It's the exact same pattern. Everybody see what I'm saying there? Well, that's weird, right? It's an eyebrow raiser, as I like to call it. That doesn't, how could that, really? It's the exact same pattern? Surely this is not a coincidence. And it's not. And again, what we have here is evidence of this deeper, more sophisticated machinery sort of stuff that's underneath all of this that, again, we're not going to actually see. But I think it's really helpful to realize that we're talking about the same pattern here on both sides, as opposed to them being just unrelated, different theorems that are just totally disconnected from each other. Okay. Here's another cool thing that manifests itself on this diagram, and that is that there is what I'm going to call a special category of vector fields. Special in that they have certain nice properties. And one is these special vector fields are gradients. Another is that, let's see here, Green's operator is 0. And let's see, how are we going to describe, what would it mean to say Green's operator is 0? Just a real quick reminder, don't forget what Green's operator is doing. Green's operator is circulation density. Green's operator measures the extent to which the fluid has kind of a rotational aspect to it. The extent to which, if you were to drop a leaf into the water, would that leaf be turning or rotating? Right? So if Green's operator is 0, that means that there is no rotational aspect to that vector field. And the word we use for that is irrotational. And then the third shared feature, same vector fields, exact same vector fields, regularity issues aside. Path independence, which means, of course, any two curves that have the same boundary points will give you the same value for the line integral. That's what path independence means. So I like to draw on the diagram what these three properties look like. It's just kind of, in my mind, kind of a nice way to keep track visually of all of the shared properties of these vector fields. And now this brings me to another little quick observation, and then I'm going to move on to the next thing before we run out of time. Notice this means that we have three words describing these special vector fields, these exactly the same vector fields. Every gradient is path independent, and furthermore has Green's operator 0, namely is irrotational. So we have three words already to describe these special vector fields. Why do we need a fourth? Right? So again, I'm going to pick on the physicists. They've got this yet now fourth word to describe the exact same vector fields. I don't see the purpose it serves. I feel like anything we want to say about these vector fields, we already have three such words. I think that's good enough. Okay. All right. This is some strategic stuff that I'll get to when we get into chapter 7. Real quick, let me show you how to find antigradients. There's actually not that much to it. If you have a vector field, it has coordinates. If it were a gradient, those coordinates would have to be partial derivatives. So that means, for example, that the first coordinate of the vector field would have to be the x partial of your antigradient. Or said differently, your f antigradient would have to be the x antipartial of that first coordinate p. And then likewise, q as the y partial would mean that the the y antipartial of q would be my antigradient. And then likewise for the others. Now, likewise for the third coordinate. One little twist is, of course, that anytime you talk about an antiderivative, you have to say plus c. But there's the awkward fact that really all you need is, technically I don't need this thing to be a constant. I just need it to be something whose x partial is 0. And that's the whole idea of I get to add this in for free, is because when I take the x partial, it goes away, right? And this still works. So, well, that means it doesn't have to be a constant. It just needs to be something whose x partial is 0. In other words, it can't have any x's in it. But it is allowed to be a function of y and z. And then likewise for these other coordinates. So what we have then is, whatever your vector field is, you write all this down. You don't forget your, what we call partial constants. And then you just try to find some function f that's equal to all three of those things. And this plays out pretty straightforwardly. So here we go. And now I'm just following my pattern. First coordinate, we take the x antipartial. Second coordinate, we take the y antipartial. Third coordinate, I take the z antipartial. These are easy antipartials. Right? A little calculus. Don't forget your partial constants. And thus begins the game. And it's a pretty easy game to play. I'm looking for a function that's simultaneously equal to all three of these things. Can I think of any function that is equal to all three of those things? Now, I'm tempted to say, ooh, I see an x squared y term. I feel like x squared y should be in here. But wait a second. That's got to be in all three of these terms. I see it there. I see it there. I don't see it here immediately, but you know what? X squared y could totally be in there. It's a function of x and y only. So it is in that third line. It's the partial constant. And then likewise, xz, this could be xz. That's fine. So xz. And then likewise minus yz squared minus yz squared. And this could be minus yz squared. Again, a function of only y and z. And so sure enough, I have found a function that is equal to all three of these things. And this is my antigradient. And you can confirm for yourselves, easy direct check. And I suppose this is a healthy exercise that everybody should do, is x partial, y partial, z partial, and confirm that it is what it's supposed to be. Okay, I guess we're out of time. Y'all can read this last example here yourselves. This is just a failure of the above method, which had better fail when there is no antigradient. So take a look at that, and we're done now with Chapter 6, and we'll start with Chapter 7 on Friday. Okay, see y'all later. Have a good one.